All right. Ladies and gentlemen, class recording for today has started. So, yesterday, we began talking about heat transfer. And to start that off, we talked about what heat was. So what is our definition of heat? Transfer of thermal energy. And why does transfer of thermal energy happen?
Why or how?
Why? Because of a temperature difference, right? And heat always, or energy flows from high temperatures to low temperatures, okay? And then yesterday, we introduced 3 ways in which that can happen. So tell me about one of those ways. Lauren?
Oh, I just know the names of them.
Well, tell me, pick one of them.
Conduction.
Conduction. What's the key thing that has to be true in order for conduction to happen? Touching, contact. What state of matter is the worst conductor? Gases, right? And so we generally refer to gases as insulators because they don't conduct very well, right? If we think about some of the questions that we didn't quite answer from yesterday, okay, that are on the outline there. So we talked about gases being poor conductors because their particles are so far apart. Okay? In the winter time, if you're cold, what do? Put on a blanket, or you put on, well, I suppose you could freeze unless you're smart, and then you like, a breathe. So, that's true, even if you're cold or not. So, okay. All right, so putting on a blanket or putting on a sweatshirt or a sweater works the same way. If you put on the blanket or a sweater, you trap some air surrounding you. Okay? Does that make sense? There's a little air that surrounds you. And your body then heats up that air because hot to cold. But because it's air, once it's heated up, does it conduct energy away from you into the blankets? Because it's a poor conductor, right? Or in the wintertime, when you dress in layers, right? If you put a long sleeve shirt on, then a sweatshirt, then a coat. Each layer that you put on, what are you trapping between your sweatshirt? More air, right? And that means what? Well, it means there's less heat transfer. Does that make sense? Because in the wintertime, which way is energy looking to flow? Out of you into the cold air, right? Hot to cold. But if you trap little layers of air, everything you put on, every sweatshirt you put on, or sweater or shirt or whatever, you're trapping a little bit of air that prevents the heat transfer, slows it down, and in theory keeps you warmer. All right? Good there? Okay. What's another type of heat transfer that we talked about yesterday? Oh, go ahead. Radiation. What's the gist of radiation, Alex? Okay, waves moving through space. No matter required, right? Meaning, do we need anything to transfer the energy from here to there? That's how we get all of our energy from the sun. There's nothing between us and the sun, but energy still gets here because of radiation. Straight waves traveling from one place to the other. Okay? And then, the third type of transfer, convection. Aaron, what's the gist of convection? So we have movement of fluid, right? Actual movement of matter. Okay? Did we talk about convection currents yesterday at the end of class?
No. We talked about fire.
Okay, so let's talk about an actual convection current. All right? So, let's go here. Let me show you a video real quick.
Is it Joe Rowell?
No, it's not Joe Rowell. This is me.
Water boiling? Awesome. We did talk about that.
So, here's the law of the land, right? And I showed you this. It was on the screen like when you guys came in yesterday, right? Okay. So, right, a lava lamp works on the gist of convection. Okay? A lava lamp has a little heating element down at the bottom. It's the glowy yellow part, right? And then it looks like the fluid comes right out of the glowy yellow part and heads upward. Okay? What does the glowy yellow part do to the fluid that surrounds it? It heats it up. Generally speaking, they're liquids anyway, right? Like they're all liquids anyway, even when you turn the lava lamp off. But generally speaking, what happens to the volume of something when it heats up? It expands, right? Thermal expansion. We talked about that a couple days ago. But if you're talking about the same yellow blob, but now it's bigger, what does the expansion do to the density? It makes it less dense. As things expand, they generally become less dense. What happens to lower density things? They float, they go up, right? So the heating element down on the bottom heats up the material, causes it to expand, becomes less dense, and then less dense things go up. But here, as they go up, they move away from the heating element. So what happens to them when they're at the top? What happens to their temperature? They cool down. And if they cool down, what happens to their volume? It contracts. And what does that do to the density? It makes it go, well, it makes the density go up, but then that makes the material go down. And then it falls back down, but when it gets to the bottom, what happens to it? It heats back up. Density goes up, density goes down, it floats, and it just keeps happening over and over again. Lauren, go ahead.
And then the fluid in it eventually just becomes so hot that they would just keep going really hot. And like
No, because so there are two fluids in there, right? Each one of those fluids has a different density. Okay? The one fluid that you see like moving up and down, its density changes more so than the fluid that is sort of like in the lava lamp. Does that make sense? It's just the right mix, okay, the blobs that you see. When they're cool, they sink because their density is greater than the other substance. But when they're warm, their density is less. Does that make sense? So there's always some of that fluid down by the heating element because the dense part of it, the cool part of it, always floats to the bottom. But then the less dense part floats up back up to the top. Does that make sense? So yeah, it's a real special mix that just by heating up that fluid that's blobbing around inside the lava lamp, you change its density enough that it's greater than the other material in the lava lamp, or it's less than the other material in the lava lamp. Okay. Good there? And that's convection. Up, down. Where else have you learned about convection? The lithosphere, the mantle of the earth, right? We talk about like plate tectonics and seafloor spreading and all that fun stuff, right? Works basically on a convection current, okay? Go ahead. A convection oven, right? The key to a convection oven is that there's basically a little fan inside of it, right? And it just keeps moving that warm air around and making sure that it all mixes up, okay? All right, good there? Say again? No, it's the same stuff. It's the same stuff, Jafar. It just goes up and comes back down.
I remember that.
Say again? No, 30 minutes, man. This is like if you want to just chill for a while, but you don't have a real lava lamp, you can just pull this up on your phone, put it in front of you, and be like,
Oh, was I right?
oh, thank goodness Jules is here. We can get started now. So. All right, the last part of this section here deals with thermodynamics. And because, and this is on the back page, okay? Because you know English, you probably could tell me a little bit about thermodynamics, right? Okay, so It deals with heat. That's the thermo part, right? The change of thermal energy. So, thermodynamics is the study of the conversion between heat and other forms of energy. Done that. So thermodynamics is the study of the conversion between heat and other forms of energy. Now, when we talk about this conversion between heat and other forms of energy, there are some rules that we have to follow. And I hope that after we go over them, you kind of think to yourself, oh, well that makes sense because of all the things we've talked about up until this point. So, we refer to them as the 3 laws of thermodynamics, right? Remember, laws describe things but don't explain things, right? But not why, right? It's what happens but not why.
AP compared to IB.
Wow. I didn't say that, you did. So, but, wow. All right, so, number 1, when we are converting heat into other forms of energy, we must conserve energy, right? I hope that makes sense. I hope we only heard it like 8,000 times already so far this year. Okay? That means that if we have a certain amount of heat energy and we're trying to convert that into kinetic energy, we can't get more kinetic energy out of it than we have heat energy into it. In fact, a lot of times we actually don't get that much kinetic energy out of it because of things like efficiency and stuff like that. Okay? But in the end, it all has to fit together. We're almost done.
Really?
All right, number 2. We talked about that heat will flow from hot things to cold things spontaneously by itself. Just like this tennis ball will fall from a high spot to a low spot. Okay? Can the tennis ball go upward?
I mean,
Yes.
It can, as long as what? We have
work being
done, right? We have to add energy into it. We can make energy flow from cold things into hot things, but only if we do work. These are, like I said, these are the laws that we work under if we're looking about transferring heat energy. When conduction happens, right, if we talk about the example from yesterday, right, we take the water from the pond to the fire, okay? That sounds familiar? No, okay. Oh, you were here, so never mind. So, okay. Never mind. Things cool down on their own, right? If we put something hot and we put it in this air, it will cool down on its own. Right? Could we make it heat up, even though it's already hotter than the room? Yeah, we could, but only if we put energy, like forcibly put energy into it. It won't heat up on its own. Okay? Say in the first one, energy is conserved. If we're converting heat energy into something else, in the engine of a car, we take gasoline, we burn it, that heat energy expands out some air and it moves the piston and that moves the wheels of the car. Okay? However much heat energy we create in the engine, the maximum amount of kinetic energy we could get in the car has to be equal to the heat energy that we started with. Right? That's the conservation part. Okay? So good.
What would happen if one of the pistons stopped moving?
Then, if one of the pistons stopped moving, the piston, like the casing of the piston, would just get warm. Right, but it wouldn't convert that heat energy into kinetic energy, which is what a heat engine does. Right? I mean, we'd still have that energy there, and things would get hot, but it wouldn't like convert it into kinetic energy, which is what a car is trying to do. And then finally, we've mentioned this idea of absolute zero before. It's the lowest possible temperature that we can reach. And we learned previously that the temperature of something relates to what? What does the temperature of a substance relate to? The kinetic energy of the particles. So absolute zero, the coldest temperature we could reach, would correspond with what? Well, if there's no movement of the particles, can that happen?
No.
No, you can't get it to no movement,
Technically,
right?
wouldn't that not be the lowest?
Well, see, that's the thing. Theoretically, right, Pat, theoretically, we could look at how much something cools down and how much the particles slow down. We can kind of draw a line and say, okay, this would be the temperature if we got to absolutely no movement, okay? Theoretically, like, you know, on a piece of paper we could do it. But in reality, to get something cold or to get something colder, what do we do? You have to put it next to something colder than it, and it loses energy, right? But if absolute zero is the theoretically lowest temperature we could go to, you can't put you can't put something colder below it because there is nothing colder below it. So it's fine, like on a piece of paper, to be like, yep, that would be the lowest possible temperature, but in reality, we can't get there.
Something is like hot, stays in space, but it not change its temperature.
In theory, no, until you interact with something else. So.
Wait, so what would that be like in Fahrenheit?
Fahrenheit, it's like minus 450 something. So in Celsius, it's minus 273. So
Is it just like zero?
zero Kelvin, right? Kelvin. We refer to Kelvin as an absolute temperature scale. That absolute zero is the lowest Kelvin temperature. So Celsius and Fahrenheit are based off of like the freezing point of water, which is important for us on Earth, but in the grand scheme of things, isn't really that special.
So like what temperature is like
1 Kelvin is like minus 272 Celsius. Right? So it's not a whole lot of movement. Okay. All right, so as far as that outline on heat transfer and thermodynamics, there are several things that we didn't answer. That's okay. All right. We will sort of answer them as we go through these things here with calorimetry, or we'll just kind of skip over them or apply them as we're talking about our lab over the next couple of days. Okay? So just because we haven't finished up that outline, let's not freak out too much, but let's introduce a couple of things here. Okay? So, as far as the next outline, the last outline in this section dealing with heat energy is concerned, we get into calorimetry. All right? So, if I tell you, hey, or if I ask you what's calorimetry, right, you're probably familiar at least with the root of the word, right?
Energy.
Calorie, right? Okay? Because calories are a form of what? Energy, right? Calories that you eat, you know, whatever you ate for breakfast this morning. You should have had breakfast this morning. You should. So, you really should. You know, your body needs energy to work, and the name of the meal, breakfast, you're breaking your fast because you haven't eaten anything all night, you know, and so you really should put something in your body to like get it going. So, yeah. I had a peanut butter and banana smoothie this morning for breakfast. So.
Those things are so gross.
Peanut butter, banana, chocolate, a little chocolate, bananas, and yeah. So. And they were frozen bananas too. So like they get that creamy. Like oh man, it's one of my favorite breakfasts. So. What? Blender, yeah. Peanut butter, frozen bananas, milk. Oh, yeah, milk. Chocolate syrup to make it look. Yeah, actually, lately I've been putting like Carnation instant breakfast because it has like nutrients and stuff, you know. And then I put like a scoop of dry oatmeal in there. It gets like chopped up and everything. Good.
Who cares? He's saving time.
Yeah.
He doesn't have to eat all those things.
But that's like, I mean, when you blend it up, it just gets chopped up real small, and you know, I can't taste it. My wife says she can taste it, but I think she's crazy. So.
You're gonna be eating it all anyway. You might as well save time.
That's what, yeah. I mean, like oatmeal is good for you, like good for your heart. It's good for your heart. It's heart health. All right, But when I asked that question, when I asked the question, what is calorimetry, to the previous class, somebody said, is it like stoichiometry? And they were being funny because calorimetry and stoichiometry have lots of syllables and they're long words and stuff like that. But when I started thinking about it, there is a similarity between calorimetry and stoichiometry in that
It goes on with
metry, yes, okay. Okay, that means like the measurement of, okay? And the reason why they're similar is because they involve numbers. Stoichiometry was the quantitative relationship of or quantitative analysis of reactions. It wasn't just what is the reactant, what is the product, it was how much reactant and how much product. Calorimetry takes the ideas of conduction and convection and radiation, that's how energy is lost. Calorimetry goes, okay, how much energy is lost? So we start getting into numbers here. Start actually measuring that energy. So let me start with this example, okay? Let's say you take a pan of water and you put it on the stove because you're going to make some macaroni and cheese or whatever it is. Okay? You got to boil the water. So you put the pan of water on the stove, you turn on the burner, fire starts, energy is being transferred into the pots that you have the water in, and then it's being transferred through that into the water that's in the pan. Okay? Good there. So, let's say you heat up that pan of water for 1 minute, 60 seconds. In most cases, that's probably not going to be enough to boil your water. But after 1 minute of that water being on the stove, could you take your finger and stick it in the water? After 1 minute? After 1 minute?
No, you could totally stick your finger in it.
Yeah, after 1 minute, you'd be fine. It might be a little warm, but you'd be fine.
What does it take? It takes like
8 minutes about.
You guys don't know that.
But Jules,
Kill the hat.
on that same idea, would you lift the pan up and touch the bottom of the pan? Wouldn't do that, right? What? Well, maybe if you're getting money for it. I'm not advocating self-harm for financial gain, but you know, you got to make your own decisions in life, I guess. But even though the pan and the water have been receiving energy from the burner for a whole minute, one showed a much bigger increase in temperature than the other one did, even though they kept getting energy for the same time. So, when we give objects energy, they don't all heat up at the same rate. And that's because of something that we call specific heat. So, by definition, specific heat is the amount of energy needed to raise the temperature of 1 gram of a material by 1 degree Celsius. The amount of energy needed to raise the temperature of 1 gram of a material by 1 degree Celsius. So how much energy do we have to take this material and raise its temperature? Okay? Amount of energy needed to raise the temperature of 1 gram of material by 1 degree Celsius. Okay? So, the lower a material's specific heat, the more the temperature will rise when a given amount of energy is absorbed. So if we go back to our definition of the pan of water, even though they're both on the burner for the same amount of time, the pan gets really, really hot, the water not so much. It's much easier to raise the temperature of the pan than it is to raise the temperature of the water. Lower specific heat values will change their temperature more quickly. And that's true when something is heating up, but it's also true when something is cooling down. So lower specific heat values mean the temperature of a substance will change fairly quickly. All right, good with these definitions? Let's talk about some situations that apply these definitions, all right? So, first let's check out this guy right here, all right? Guy eating a piece of pie. Why he's not using a fork, I'm not sure.
I don't know how his pie stays together.
So yeah, how does that pie stay together? I mean, I guess it depends on what kind of pie it is. Like if it's like I think it's like a lemon meringue pie that has like that jello-y stuff, you know? But yeah, like if you have like an apple pie.
An apple pie.
Yeah, it does look like an apple pie. Just on an unrelated note, not that I want this launch into some unrelated conversation here, but back in college, we had like dorm Olympics, you know, like we compete against other dorms, stuff like that. And one of the things was we had a pie eating contest. I was never part of the pie eating contest team.
Were you use your hands?
Yeah, you could use your hands, but what we would do is you'd take, I don't know, like a 9-inch pie or whatever, like a normal sized pie, and there were 4 people on the team, and they just cut it like in quarters, and each person had to eat like a quarter of the pie. Well, if you're trying to go fast, right? We had this one guy who could eat a quarter of a pie in 2 bites. Like you didn't have to digest it. You just had to put it like in your mouth. So he would take his quarter of the pie, like a whole quarter of the pie, and he would bite like wham, like take the whole like front half off, and then he would turn it sideways and just like stick the rest of it in his mouth. Boom, done. Like, so anyway, all right.
What part of the contest were you part of?
Who won the Olympics?
What?
Who won the Olympics?
We won one year when I was there.
Out of what
Other
school?
rival.
Where'd you go?
I went to Case Western Reserve. So. What? Yeah, I mean, probably wasn't as fun as maybe some other places. But.
What events did you go to?
I was part of. We had to make a pyramid, like a pyramid stacking. You know, like a human pyramid. You know, I did that. That kind of sucked sometimes because I wasn't on the bottom. We had to make it was 15 people, so it was like 5, 4, 3, 2, 1, right? And I was on the 4th row, so like, and like the way it happened was you didn't just like build the pyramid. They had 2 chairs with like ropes, and you had to like start on like where the fume hood is. And you had to crawl underneath the rope, and like the other rope was here, so you had to like crawl like 20 feet and then build the pyramid. So that was okay. Like the crawling part was all right. But I wasn't on the bottom, I was on the 4th row, but then we're going fast, so the people who were in the 3rd row, they would jump on top of me, and like, sometimes their knee would catch you right in the spine. That was a good time. and then there's like more people on top of them, so like, yeah, it was fun. College. And then we had like a tug of war too, so I was on the tug of war team up here, so.
Whoa,
Yeah. So
was Case not college?
Oh, it was a good time. You know, maybe a different kind of fun. You know, I mean, there was still fun things to do. Anyway, so specific heat. Well, not this kind of pie. You ever get one of the apple pies at McDonald's?
Yeah.
They come in that little box, right? Yeah, they're not real good. All right.
Or pies.
What? Or pie. They're not real good. Or pie. So. Or you know what kind of the grossest one, like gross and like if you think about it, but they're really good. You know, like those Hostess pies that you get in the you know what I'm talking about?
Yeah.
If you ever read the nutritional facts of one of those things, it's like that little pie is like 1,000 calories. Read it. It's so good, but. It's like 1,000 calories and 20 grams of fat. That's why it's so good, probably. But you know. Anyway, so if you look at the package, it says right on the package what? Caution, filling may be hot, right? Or if you think about a couple other things you might be a little more familiar with, you don't eat McDonald's apple pies, right? If you've ever made a Hot Pocket at home, right? Or the Ninja Assassin of after-school treats, pizza rolls. And why are pizza rolls the Ninja Assassin of after-school treats? Because you put them in the microwave for whatever you're supposed to cook them, and you pull them out, and you let them sit on the counter for, 2 minutes or whatever, and you pick it up, you're like, oh, everything's good to go, and you pop that bad boy in your mouth, right? You take that first bite, and now there's lava inside of your mouth. Like wait a minute, that was perfectly cool when I picked it up, and now there's molten rock in my mouth. It's basically the core of the earth in my mouth, right? So, yes? What's it? Yeah. Well, actually, that's actually kind of good that sometimes they're cold on the inside, right? They feel warm on the outside, but they're cool on the inside, right? Or another thing too that this is kind of a notorious thing. If you ever had beef stew that has like big chunks of potatoes and carrots and stuff, right? Like, so the beef stew's all good, the carrots are all good, the mushrooms are all good, and then you get one of those chunks of potato, and you bite into that thing, and it's basically like a 5-alarm fire still inside of the potato. Like, wait a minute, what happened here? It all has to do with specific heat. The inside of the pizza roll has a different specific heat than the crust of the pizza roll. So, it takes longer to cook the inside of the pizza roll. That's why the outside might feel warm, but the inside is still cold. It takes more energy to heat up the inside. But once you've heated up the inside, it takes longer to cool down. So the outside may feel cool, but the inside is still really, really warm, right? So the filling of the pie or the filling of the pizza roll or whatever we might be talking about here, right, is still hot than the crust because it has a larger specific heat. Remember, larger specific heat values are harder to change temperatures. They're harder to heat up, they need more energy to heat up, but they also stay hot longer. Larger specific heat values. They're harder to heat up originally, but they stay hot longer once they already are heated up. Or just to make us think of funner times, right? Okay. So if you go to the beach in the summertime, right? Maybe you're sitting there on the beach, and maybe you're not really into going into the water because it's like eerie, right? Trash. Bacteria levels might not be safe, that kind of stuff. So you sit on the beach, maybe underneath an umbrella, you're reading the book, right? But you decide, okay, I've been here, I need to stretch my legs out a little bit. Maybe I'm going to go put my feet in the water. Not submerge myself in the water, just put my feet in, right? Well, underneath your umbrella, everything's cool, but then you step on the sand outside of the umbrella that's been in the sun all day. The surface of the sun, basically, they're basically the same temperature, right? But then you walk or you run gingerly to the water and you step in the water, and it's not that hot. Right? It's still cool. Even though, maybe step on the glass or a syringe or something. What, you step on a syringe in the lake?
No. Like when you walk back to your umbrella, your feet are like dry.
Yeah, so, right? The sand and the water have been in the sun for exactly the same amount of time. they have received, right? They've received exactly the same amount of energy, but the sand is much hotter than the water because water, higher specific heat, right? Higher specific heats are harder to change temperatures.
Oh, at least like a water. I just figured on the same exact thing.
Say again? So, if we talk, Ronnie, if we relate these things to insulators and conductors, right? We want the pan that you cook things on the stove to heat up very quickly because we want it to transfer energy into the water. So generally, conductors, we want to have lower specific heat values because we want them to heat up real quickly so they start heating up the things that are in them. But insulators, we want to have lower specific heat values because we don't want them to heat up as much. Right? Specific heat is the quality of something that determines whether it heats up quickly or doesn't heat up very much. Okay? So, to understand, let's finish people writing this down, then we'll talk this last thing, and then we'll call it a day. Okay? And Ronnie, I'm going to ask you this question because you're good at answering this question. Okay? Hold on, let me just finish this last thing without everybody putting their stuff away. All right, so Ronnie, 2 factors that determine the state of matter of something, right? What are they? Attractions and energy. If something has a really strong attraction, hey, can we stop please so that people can actually hear the answer to the question? If particles have a real strong attraction, if we add energy, energy makes them move more, right? But if they already have a real strong attraction, it's hard to get them to start moving because they're really attracted to the thing next to them. Water has a really strong attraction for other water molecules. They're closer together, but also, too, if we add energy to water molecules, they don't move as much as other things because they're really strongly attracted to the molecules that are next to them. So we have to add more energy if we want to take them and break them apart and make them into like a liquid or a gas. Does that make sense? So that's where we'll start tomorrow with why is water so high on the